All right, now that we have a basic understanding of what projectiles are, we're going to start looking at a little bit more detail of the different types of projectiles. Remember, just a bit of active revision. In the last video, we classified projectiles into three main groups. Now, can you recall what those three main groups were? Now, those three main groups, of course, was just pure vertical examples where you can be dropped from rest or thrown up in the air. And then there was horizontal, and then there was at an angle. Now, we're going to be looking at those in more detail in this video here and adding a little bit more about when they're done at an angle, how can we calculate components. So we're still on this dot point here. But now, other than just looking at these two, which we did in the last video, now we're coming back to look at this section here about vertical and horizontal components. So let's get into it. All right, so the most simple type of projectile, of course, is 1D motion, where we just got one axis. And in this case, it's the vertical axis, it's the y-axis. So when we look at 2D motion, we're going to be breaking up the velocity and acceleration and lots of other parts of motion into an x and a y axis, so 2 dimensions. But here, the most simple one is 1 dimension. And so, for an example, dropping a ball from rest is just 1D rectilinear motion. Remember, we did that back in Module 1 in kinematics, 1D motion. And of course, we're going to find out that we can, of course, use our Suvat equations for that as well. But some things, key ideas to remember here, that it's always got gravity acting upon it downwards. Now, for me, I have a coordinate system where I say down is negative and then up is positive. Okay, that's the coordinate system that I use. So therefore, the value for G would be minus 9.81. Now, it doesn't really matter. You can use the reverse of that. You can make positive going down and minus going up. As long as you're consistent with your vector signs, then your calculations will work. But for me, I've put mine as going down. So we've got an acceleration, which is a vector quantity. It's got magnitude and direction. So the magnitude is 9.81 and the direction is minus. Now, it's always acting down, always acting down. So if we start with initially with the initial velocity at rest, I can write that in there. It's got 0 velocity in the y direction. But as I let it go, gravity acts upon that, and so it starts accelerating downwards by this amount here. And as you can see, the distance it has between them gets bigger and bigger because it is accelerating, therefore its velocity is increasing, and it's traveling more distance in the same unit of time. And so we can see that the displacement, or I should say the distance between the balls, increases. Okay? Then we can have it just going up and back down, so we're just throwing it straight up and then catching again. It's still 1D motion here, and so we know that gravity is still acting downwards by the same amount. So even though as soon as that ball leaves my hand, it starts to slow down because gravity's acting in the opposite direction, okay? And so if I was to draw that in with a color here, then as the ball goes up, it's got acceleration acting downwards by the same amount each time as the truck goes down the highway. So that's the acceleration vector. If I was to put the velocity vector, it would start off very high because it's being thrown at a certain velocity. The next one's going to be smaller because, of course, it's slowing down. Gravity's acting in the opposite direction. Up the top here, momentarily it stops, so it has no velocity in the y direction. And then, of course, it starts coming down again, okay, and then until he hits the ground. Okay, so we have to remember this key idea here that acceleration is always acting downwards by the same amount each time. The velocity in the y direction initially is very large. It then starts to decrease, and then up here it becomes 0, so I can write Vy equals 0 up the top there. And then once after that, it starts increasing again, but it now has a negative sign because remember, downwards is counted as negative. So all of these things are fundamentally really important to understand now, so write these down, because when we start to do calculations or when we start to graph them, the size, the magnitude, I should say same thing, but it's the magnitude and the direction are things that we need to take into consideration. All right, the next type is, of course, horizontal projectiles. And so with a horizontal projectile, we have two separate components now. We have gravity always acting downwards, so we have an acceleration acting downwards, but we also have now a velocity in the x direction. So if we have a cannon here, that cannonball will fire it like this. Now let's link this back to Newton's first law of motion. Remember, Newton's first law of motion says that once an object is in motion, it will stay in motion in a straight line unless it's acted upon by an unbalanced external force. Well, if we had no gravity, it would go in a straight line, according to Newton's first law. However, because we now have gravity acting upon it, remember, gravity is the only force acting on it if we ignore air resistance. So even though this ball is now in motion due to its inertia, gravity is acting upon it, which means it starts causing this unbalanced force and starts changing its direction. And so what we can see is the ball starts now going downwards like this in a parabolic path, right? And so we have a horizontal component. It's always traveling towards the right, okay? So it's getting further and further away from the edge of the cliff, but it's also got a y component. It's now starting to go downwards, so its velocity is increasing in the y direction. And so we can break our motion up into an x direction. Initially, it has a velocity given by the cannon or the hand or whatever it is. Ignoring air resistance, its velocity remains unchanged. So very important, velocity remains unchanged in the x direction. So these key ideas here, make sure you've got them down, make sure you're highlighting them, and you're thinking about these every single time you do a projectile problem, because that's what they tend to test in calculations. I've got to remember that the velocity in the x direction is the same as the initial because it doesn't change. So remember these key ideas. Then if we look at the y direction here, the y direction, right, initially it has no velocity in the y direction. So when it's in the cannon and when it just comes out, it has no velocity in the y direction because gravity has not yet acted on it to change its direction. However, as soon as it sort of leaves the cannon, 1 millisecond or so after that, it now has gravity acting upon it because it's a projectile, and therefore now it starts to have a value for the y direction velocity. Okay, we've said that object accelerates, and that's because it has g acting on it, and we can see that shape like so. Okay, so there are key features there that you need to realize and add to your mind map. Alright, now let's look at the third class, which is of course the parabolic motion. And so here we've got 2D motion going on. We've got an x component and a y component. And now we're actually having a ball being thrown up at an angle as opposed to just being pushed to the horizontal direction towards the right. Now notice that we have two dimensions, of course, here. The vertical motion, just like our last two examples, is in the y direction. It has a constant force of gravitation acting down, so you can see that in my diagram. I've got my arrows showing you acceleration due to gravity, and notice the arrows are all the same size, right? So it's a vector, it's the same size, minus 9.81. We have a velocity constantly changing. Now, how is that possible? Think about what we talked about before. We said initially it will start off with a large y component. But of course, as it's going upwards, gravity's pulling it down, so its y velocity decreases, right? So if I was to draw in my y velocity, I can have my y velocity being big, then it gets a bit smaller, gets a bit smaller. Of course, here we know Vy is equal to 0, so it has no velocity. And then now it increases its velocity in the x direction, in the y direction, and it gets bigger. Okay, so have a look at what I've done there. It's now in the opposite direction, and it's getting bigger, just like we did when we just held a ball there and let go. Acceleration is occurring. Okay, in the horizontal direction, same as what we had before with our cannonball, right? There is no acceleration in the x direction where we're ignoring air resistance. Remember, acceleration does not necessarily just mean it gets faster, but it can get slower. It's a change in velocity. So if we're ignoring air resistance, then it's not slowing down. And of course, it's a projectile, so it's got no propulsion. It's just going with its initial inertia. So it will not speed up, will not slow down. It will maintain its velocity. Okay, and therefore its final velocity in the x direction is the same as it was when it started. And we can see that there. We can see my blue arrow showing you that the velocity in the x direction remains constant throughout the flight. Let's quickly now, before we finish, right, talk about how do we do components, and when they're at an angle. We can see here we've got a golfer in a bunker. Unfortunately, that is a viewpoint that I tend to see more often than not. But you can see with the golf ball, when they're hitting it, it's following a trajectory that is parabolic. And so we can work out the x and y components by using some trigonometry. We did this back in module 2 with dynamics. We did it with forces. And that same understanding can be used here to do it with projectiles. And so we used trigonometry, if you remember back in module 2. Okay, we had our hypotenuse, our opposite, our adjacent, and of course our angle there. And when we set up that, we can actually find out the components of our velocity vector. And so here we have our velocity vector of the golf ball being hit with 80 meters per second. That's u, so it's the initial velocity there. Of course, that has a vertical component and it has a horizontal component. And we know through having done this before that we can break that up into sine and cos. So the x component is cos. We know that cos is adjacent over hypotenuse. And so when you write that down, we can see it over here, that is u x is equal to 80 cos 35, and it gives us a value of 65.53 meters per second. We can do the same for our vertical component, so that is opposite over hypotenuse, and then we end up with a value for the vertical component. And so those two are the components of the velocity. Now it's important you know how to do this, because of course, just like back in dynamics, sometimes you need to find the final velocity, and we need to add these components together to find the final velocity. And of course, because it's trigonometry and it's a right angle triangle, we can use Pythagoras. And we're going to look at that in later videos. So that's it for this video. We looked in a little bit more detail the different major categories of projectiles, so vertical, horizontal, and at an angle. We reinforced those fundamental ideas, which hopefully should now be starting to be ingrained into your brain, that in terms of gravity is always acting down at the same magnitude. We've looked that the x component velocity does not change, y it doesn't change. We related it to Newton's law of inertia. And so these are the things that you need to practice in an active way. The key points that you've taken from this video, now you need to do it actively, draw it out, talk it out, and try and make these links between every single video we do and every single question you do. Because if you do that and add it to your mind map, you're constantly reinforcing the underlying concepts rather than just trying to memorize what's going on. And use some unusual things to get it in your head. So use things around the house, in the classroom, to constantly ask questions about the motion, and use your notes and your knowledge that you've just gained to explain that motion. And do that every time you do a question. When you do our problem sets, okay, you can use, of course, the study cards as well. They're available on the website if your school doesn't subscribe. And of course, you've got your projectile motion posters to give you a visual understanding of what's going on. So here we've talked about our golfer, but we haven't talked about volleyball. So apply it to new and unusual situations to force your brain cells to think about those underlying concepts. Hope that makes sense, and I'll see you in the next video where we keep exploring projectile motion. See you then.